Okay, so good evening. Am I audible and visible?
Yes, madam.
Okay, thank you. Okay, so good evening, everyone, and welcome to today's live session. And today is week 12's live session, and this is the last live session for the course Nonlinear Vibration NOC24 ME54. And I'm Rashya Aditi Ranjan. I'm an NPTEL PMRFTA, and I'm also a PMRF scholar in the Department of Mechanical Engineering, IIT Patna. However, I would like to mention that I have kept extra session tomorrow from 5 to 7 p.m. You people must have got the mail that the schedule of the session. So there I'll be giving a revision of whatever we have learned in this course. Along with that, I'll be open to take any of the questions or doubt if you people have. Okay, so coming on to the overview of this week. So, application of nonlinear dynamics. So, since the last two, three live sessions, we were actually discussing about the applications of nonlinear dynamics or the applications in physical systems. Like this week, it was focused on the manufacturing processes and how manufacturing processes have nonlinear phenomena and everything. Okay, so that was discussed. Apart from that, a very important thing that happens in case of manufacturing process, which is known as chattering, was also discussed. So this week it was focused on manufacturing process, right? Last week we discussed about beams, and we were actually discussing about viscoelastic materials, and before that we were discussing, I guess, about the vibration dampers and everything, right? So manufacturing processes. Apart from that, chattering was discussed, and what chattering is, what is the effect of chattering, where chattering comes, everything, these things were discussed, right? And apart from that, Sir also discussed about some of his papers or some of his PhD scholars' papers, that how they have actually modeled the system and then how they have performed the nonlinear analysis in order to find out that what the system behavior is going to be, right? After that, chaos and its control were discussed. Okay, so chaos, we know what chaos is, right? It's an aperiodic motion, right? We have done numerical simulations to see what chaos is, right? Chaos means not periodic, simply. If either my system behavior is going to be, it is going to have a fixed point, it is going to have a periodic behavior, it is going to have a quasi-periodic behavior, and it is going to have a chaotic behavior, right? So the question arises is that why do we need to control chaos? Right, if the chaos is there, let it be. What is the point of controlling it? So if you people remember that I have discussed also and I have shown through numerical simulation also with example of some systems that in case of chaos, my system is highly sensitive, isn't it? If you remember that in case of a my system solution could be of four types, right? Fixed point, periodic, quasi-periodic, and chaotic. So among them, these three behaviors, right? They were not sensitive to initial condition. Now, when I'm saying sensitive to initial condition, what do I mean? I mean that if I give a small variation to the initial condition, Okay, small variation as in delta x naught. I It is suppose 10 to the power minus 6. This is your small variation in initial condition. If you people know that the basic definition of sensitivity, it comes from that if we give a very small variation in the input, how is my output going to vary, right? So similarly, we define the sensitivity of these possible solutions of a system, right? In these three cases, the sensitivity is not that much, right? Like what I mean is if I give this small variation delta x, my system is still going to show the same solution. If it is having some periodic trajectory for, let us suppose, the initial condition x naught, then it is going to have the same periodic trajectory for the initial condition x naught plus delta x. Same is the case for quasi-periodic and fixed point also, and this I have shown through numerical simulation also in my previous live session. Okay, but in case of chaotic motion, if I give even this small variation in the initial condition, my system is going to diverge a lot after a certain period of time, right? So, which means that if I am physically using my system, right? So, what will I do? What do? I design it on the basis of how it is going to behave, right? So, if I design it for a particular kind of chaotic behavior, let us suppose that the system is going to have, let us say, I give it some A name. My system is having some A strange attractor or A kind of behavior for the initial condition x naught. X naught dot, this is my solution, which is chaotic. Okay. Now you see that we as human, how much can we have the variation? Like if I have to give the initial condition on myself. It may happen that I'll, instead of giving it as 2 mm, maybe I can give it as 2 plus 10 to the power minus 6 mm. That is possible, right? This amount of error can anyways be introduced in the system by human error, by machine error, by any kind of an error. Okay, this is possible. But if this much variation is introduced in my system, my chaotic behavior is going to change to some B, which is also chaotic, but it is different from A. Okay, it is for the initial condition x naught plus delta x naught. I've kept the velocity same, just some minor variation in the position. It led to some other chaotic orbit, right? So now, if my system is so much sensitive to chaos, the best way to deal with it is to avoid it, isn't it? Because either I'll have to give a lot of computation cost, I'll have to give a lot of cost to the precision and everything of the machine so that I can get a proper chaotic motion for a proper initial condition. However, even the precision, if you people remember, I showed you for the variation of 10 to the power minus 12 also, the system was showing different behavior, right? Till how much precision can I go? Right. So it is better that we avoid chaos and we use the system only for the fixed point periodic and quasi-periodic. Now, see, when we model a system, right, what do? We consider some whatever the mechanical relations are or whatever the chemical reactions are, electrical, magnetic, whatever. If we consider it, we form a differential equation that defines my system dynamics. Correct? So, for that case, when I define my system equation, is it possible that I consider everything? I mean, obviously, I can consider, but it becomes very difficult, right? We usually have some kind of assumptions, right? So, since we have these kind of assumptions, it is not going to give me the proper and realistic behavior of the system, correct? So then what will I do? The only option I have to deal with a nonlinear system is that I find its equation of motion, I do the analysis, and I get to know that whatever the parameters are, how the system is going to behave with what parameter, and then I can just work with the parameter which will give me the required solution. Right. But that is not possible always. Also, there could be some kind of a noise or some kind of uncertainty in the system, which is possible due to the environmental condition or due to some kind of an error. So in that case, what do we do is we control the chaos. Okay, we try to control it. Now, controlling, I mean that, okay, I know that my system should be like, for example, I want to do a particular, like if I want to use like the as the example has been discussed with you people of that of a artificial muscle, pneumatic artificial muscle. So if I know that okay, this I want my artificial muscle to contract from 4 mm to 2 mm. So I know how my system should be. Okay, so I'll give it the reference signal, and now the work is of the control system. Now the control system is going to take care of everything. It is going to vary the air pressure in such a way such that my desired output is going to reach. I hope that this is clear. However, I'll discuss about chaos and chaos control when I'll discuss the questions also. Okay, so let us come to the questions. See, this week's your assignment is also very easy, and I'll be taking up only some questions which would make your idea clear, and then I expect that you people will be able to solve it. Okay, now see, which of the following is related to the chaos control of a system? Okay, so firstly, chaos control means, what does chaos control mean? Now you could ask me that why would I write reducing the sensitivity of the system? So this basically means it is the objective of your chaos control, reducing the sensitivity of the system. When I say chaos control, it does not always mean that I want to avoid chaos, right? Because avoiding chaos means that I would have to give a lot of work to my system, and then only it can avoid chaos, right? And in order to avoid chaos, my controls, first I'll just give a brief about control system. So it is used to get the desired output from my system by controlling the input. Because every system works in that way. We give it an input, it gives an output. Right. So my control system is now going to control my input. Now I am not controlling my input. The input to the system, I am not controlling. Now my control system is going to control. But I'll have to design my control system so that it will be able to achieve whatever I want, right? So now control system is further divided into two categories. One is your open loop control and second one is your closed loop control. So open loop control, by open loop control, we mean that, okay, we give it a particular signal and it is going to perform whatever it is going to perform, whatever for the input. Like for example, fan, we have fans, right? We give it some input and then it is going to rotate, right? So depending upon, like for example, I take a table fan and first I'll keep it in my room and I'll just switch it on. So it is going to give me some wind or air, some kind of. And now if I take that fan and I'll keep it in some, let us say, very a day where there is wind blowing at a very high speed. At that time, if I switch on the fan, it is not going to give me the same speed as that when I use it in the room. Correct. However, my input is still the same, right? But depending upon the external condition, the performance of my fan is going to change. Okay. So this is a case. And second one is your closed loop control. Now, when I talk about a closed loop, for us, this open loop control, one example that I would like to give is that of a washing machine. So, if I want to wash my clothes in my washing machine and my like clothes are very dirty, okay. Now, I'll put it in my washing machine. I'll set the time, right? I'll set the time that okay, the washing machine will operate for, let us say, 20 minutes. What will the washing machine do? It will operate for 20 minutes and then it is going to stop. Is my washing machine going to check whether my clothes are free of dirt or not? Whether my clothes are cleaned properly or not? Whether my clothes are germ free or not? My washing machine is not going to check me until and unless I have a very advanced washing machine. If I talk about the washing machine that I used in normal Indian household, it is not going to tell me. Right. So what is this? This is a open loop control. I or the machine has given it command. Like if you see that there are now automatic machines in which you have to just select that what kind of a clothes it is, whether it is woolen cloth or whether it is cotton cloth. And then if you give that as an input, they are going to set the time and the amount of surf it is going to use. They are going to use it. Okay. Take it as an input. But same that it is not going to check whether my clothes are being washed properly. They have been washed in that particular time with the particular amount of surf or not, right? So this is my open loop control. Now, if I talk about a closed loop control basically means that my system's output, I'm always having a track of my system's output. Okay. By that, what I mean is that I apply some sensor at the output. I take up the value of output and then I give it to my controller. Now my controller is going to compute that okay, I've given it some input U corresponding to which it should give some output Y, but it is showing some output Y1, which is not correct. And let us say that maybe I should write it. Input is U corresponding to which the system. Okay, this is the ideal case. But the output is y1, where y1 is less than y. So now what would my system do? Definitely my system is going to increase my input, isn't it? For a linear system, if I talk about a linear system, this time I'm not talking about a non-linear system because in non-linear system, there is not a monotonic relation. We have understood this after learning this course that non-linear system is not going to have a monotonic relation between the output and the input. However, my linear system is going to have. So if I consider a linear system over here, then my input is going to increase my u, which is the input, so that my output increases and reaches, and it is going to keep increasing input until and unless it reaches the desired value y. Now this is my closed loop control. Okay, so closed loop control, like for example, you can see it in your automatic ACs that have the option of power cut, wherein if you will set the temperature that okay, my room should or my ambient should have a temperature of 25 degrees Celsius. So as soon as the sensors that are there in the air conditioner. As soon as it is going to sense that, okay, now your temperature of the ambient is 25 degrees Celsius, it is going to automatically cut off the power of the AC. And then it will again start the AC when your temperature will go to, let us say, 26 degrees Celsius. Not Celsius actually. Okay, let us say 26 degrees. Let us just keep it dimensionless as of now. Okay, so this is your open loop and closed loop control. Okay, now as I said that when we are dealing with a nonlinear system, we have the way by which we can use the system is that we do the dynamic simulation. We first model it, we do the dynamic simulation, and then we get to know that what are the weather parameters are, what are the environmental conditions that should be given to the system in order to behave it in a particular manner. However, there is always certain assumptions, or I can maybe make a model that does not have any kind of an assumption, but it is very difficult. And difficult along with that, even if I am able to make the model, it is also very difficult to simulate that model because it is going to cost you a very high computation time, right? So that is why we try to switch to control systems. Now see, when I have a closed loop control, you see how much my uh, hard work has reduced. Initially, I was designing the system, modeling it, analyzing it for every possible. I had to analyze it for every possible input. Okay, it would take a lifetime to do that because there can be infinite number of combinations of the input. It could be constant, sinusoidal, square, chirp sign, or maybe a combination of all these, many more random signals, everything, right? But if I have a closed loop control, the thing becomes very easy for me, right? I would just give my reference signal to the controller and rest of the work my controller is going to do. However, the controller is to be designed by me, right? I have to design my controller depending upon what my system is, what kind of a behavior it could use, what are its mechanical properties, and what is going to be my input, what is going to be my output, right? So that is the thing. There is where chaos control comes into the idea. Okay. Now, by chaos control, by using a control technique, what would I do? I would try to control the chaos. The problem with the chaos is it is very sensitive. I will not be able to control the system, and I cannot expect that my system is going to have the same kind of a behavior for even a very small variation in the initial condition, right? So now chaos control is further divided into two categories. Okay. Your chaos control is divided into two categories. Okay, the first one is your stabilization, and the second one is your synchronization. Now you would ask that what is stabilization and what is synchronization? So these are two aspects of chaos control. Okay, first is your stabilization. Now stabilization has further two types. First one is your regulation, and second one is your tracking. Now suppose, now by stabilization we know that my this kind of a chaos control is going to stabilize the system to a fixed point or a reference signal. Okay, whatever be your initial like the behavior of the system, my stabilizing chaos control is going to stabilize my system to either a fixed point or a periodic periodic reference signal or maybe quasi-period or whatever the reference signal I would like to define. The thing is that it is going to keep the system on that particular trajectory. Okay, now my stabilization has further two types. Okay, your first one is regulation. Now, in case of regulation, what do? We regulate the motion of the system. Okay, we regulate the motion. We try that my system does not go into chaos. It is never going to go into chaos. I try. My system is going to stabilize at a particular fixed point, or the fixed point could be stable or unstable both. Remember. Okay, if you remember that when we were talking about the system's behavior, we talked about the equilibrium points that my system could even have multiple equilibrium points because it's a non-linear system. It could have multiple equilibrium points, right? My linear system is going to have only one equilibrium point, but my non-linear system could have multiple equilibrium points. Now, for example, if my system has two stable and one unstable equilibrium point, then what is going to happen? Okay, for some parameter value, it may happen that my system is going to go into chaos, right? Like, for example, if I take a case that there's a system or I have a muscle, okay, artificial muscle, let us say, and I want that my artificial muscle is always will always have a length of, let us say, 1 mm. Okay, I want it to always have a length of 1 mm, whatever be the forcing that is being applied on it. Okay, what does this mean? This means that if I increase the force or if I decrease the force, if I change it from a constant force to a sinusoidal force, whatever happens, whatever is the loading condition of the system, I want my system to always have a length of 2 mm. Now, how am I going to achieve it? I'm going to apply a control strategy on it. I'm going to give my reference as 2 mm, and then my control system is going to regulate the air pressure in such a way corresponding to the forcing that is being applied on it, that my system is always going to have a length of 2 mm. I hope that you people are able to understand what I'm trying to say. Okay, so this is what is meant by regulation. So in regulation, the state of the system is regulated in such a way that it stabilizes at a certain point. Now that depends on me whether I want to stabilize it to a stable fixed point, unstable fixed point, or any arbitrary point. Okay, that is totally on me, right? Now this was your regulation, right? Now if I talk about the second type of stabilization, which is your tracking. Now see, in case of regulation, I wanted my system to be always at a fixed point, right? By fixed point, I don't mean a equilibrium point. I mean a certain point. Okay. Now, what happens in the case of tracking? So let us suppose that now I want my artificial muscle to keep oscillating with a certain frequency and a certain amplitude. And then again, I have applied a force on it, and that force could be constant. It is random. Let us suppose that it is random in nature. So in that case, what is going to happen if it is random in nature? So if it is random in nature, it may happen that my system is going to encounter chaos. In previous case also, my system could encounter chaos, but I wanted to behave in a periodic manner. So then what is going to happen? So in tracking, I would give a reference signal to my controller. I would predefine the reference signal, which could be sinusoidal, square wave, or any kind of a wave that I want, which is not necessarily periodic. It could be aperiodic or whatever behavior I want my system to behave, depending upon the application, right? So then I would choose in that way, right? I would give the reference signal, and now again, my controller is going to control the air pressure in such a way such that my system always follow the reference trajectory that I have given it, right? And it is always going to follow that reference trajectory and never going to encounter chaos. Okay. So in case of tracking, what happens is system tracks the desired or reference trajectory. Clear? I hope that this is clear. Apart from that, there is another thing that comes into chaos control, which is your synchronization. Now, what do I mean by synchronization? See, synchronization simply means that I have explained you earlier also that my system has, when it is in chaos, when it is in the chaos area, then a very small variation in the initial condition would take my system to a different trajectory, right? A different kind of a behavior after a certain time. So in that case, if I want that okay, this sensitivity towards initial condition of my chaotic behavior, I want to reduce it. I want such a controller by which even if there is small variation in my initial condition, my chaotic behavior is going to be the same. My tractor is going to be the same, right? I want that kind of a behavior. Like for example, in case of a stabilization, I was using a controller in order to regulate or track for the regulation or tracking of the system, right? But you see that in case of regulation or tracking, my system would require a constant input from the controller. The controller would work uh, continuously and it would take high computation every time, right? But what if I want my system to behave how it is behaving? But I just don't want my system to have sensitiveness towards chaos. I want chaos. I want my system to have chaos. I just don't want that it shows this much sensitivity towards chaos. Then I use synchronization. In case of synchronization, my system is going to take, like for an initial condition, my system is having some A kind of attractor. Okay. And now my controller is going to take up that. And when I'll now vary my initial condition, let us say x naught, by adding some delta x naught or minus some delta x naught from there to there, then in that case, now my controller is going to synchronize my system towards the same attractor that was there when my initial condition was x naught. So in this case, my sensitivity of the attractor or the chaotic behavior towards the initial condition has been reduced. Correct? I hope that it is clear. So this is what we do in case of synchronization. So in this case, we try to make similar behavior, or should I say synchronize the behavior of different attractors. Okay. So now if I come back to the question says that which of the following is related to the chaos control of a system? So all the first three options are correct. Okay, coming on to the second question. Which of the following is correct regarding chattering? Now, the first question is what is chattering? So if you remember that as it was explained also that what chattering is. So chattering is basically your undesired vibrations that can be seen in a system. Right? Like it is usually seen in manufacturing processes, like in case of cold rolling of sheets, it may happen that the chattering could be seen. So these are the unwanted vibrations. Okay, so wait, first I'll write chattering. These are the undesirable vibrations. Okay. Now, if I talk about the rolling process, so my rolling is the process. If you know that rolling process is used to usually like if I give it a sheet like this and I apply two rollers like this, it would compress these sheets in this way and then it would reduce the thickness of them. Right? These are my rollers. So this is your rolling operation. Okay. Now, this rolling is further divided into two categories like hot rolling process and cold rolling process. So, in hot rolling process, your workpiece is basically heated up above the recrystallization temperature, and in case of cold rolling, it is usually the rolling operation is performed usually below the recrystallization temperature, or you can say at the room temperature. Okay, so chattering is observed in these kind of rolling. So, but the question arises is that how is the chattering happening? Why is it happening? So, I'll just draw an exaggerated view. So, let us suppose that this, if I zoom it, is something like this instead of a straight line. Okay, so then what is going to happen? Now, if my roller is like this, my roller is smooth, however. Now, I'm assuming, however, my roller cannot always be smooth. It could have some kind of these kind of a irregular behavior also. Okay. So for now, if I assume that my roller is smooth, then what is going to happen? If you see that for the cold rolling process, firstly for the hot rolling process, you people know that if we like if I consider a metal and if I heat it, it becomes ductile, it becomes soft on heating, right? But if my metal is very cold, it is very hard and it has I would not say that it is brittle, but it is relatively less ductile when as compared to the material when it is heated. Okay, so now if I apply a roller on it, now my sheet is going through the roller like this. So in that case, it may happen that because of these kind of a trajectory, my this roller, instead of following a straight path, it is going to have some this kind of a vibration, right? The same could happen if my roller, if my this is straight and if my roller is not straight by wear due to manufacturing defect or due to less precision, it may happen that my roller is not smooth. My surface is smooth, but my roller is not smooth. Then also it can have these kind of a vibration trajectory. This is my expected trajectory, and this is my actual trajectory. Right. So in that case, this kind of vibration, right? This kind of vibration that is introduced in my roller is known as chattering. Okay. And this should be avoided because see, if my tool is going to vibrate in such a way, it could give many kind of, you know, deformities in my material. Okay, it could not make it smooth. There would be variation in the gauge line, which I'll discuss in the next question, however. So this is what chattering means. Okay, this could also be observed in milling operation, like in milling operation, or let us say that I have a tool like this, and then I have a material like this, and this is now cutting my material something like this. Okay, so this is the torn out portion, and this is the material, and it is going downwards. So, and this my material is fixed, right? So in that case also, it may happen. Okay, so if my this material is fixed, in that case also, my chattering could occur. And eventually it occurs also in milling operation also, chattering could be seen, right? So in here also the actual trajectory should be like this. However, the tool moves like this. So these are some unwanted vibrations that are introduced in the system, which could be due to many defects, like defect in the tool, or if the tool has been used for a long time, it wears out, or if my material is not, like my material is very uneven, or if my material is not fixed properly, my material is very loosely fixed, my tool is not fixed properly, it is loosely fixed. These all are going to lead to your chattering problem. Okay, so and it would give some unwanted vibrations. Okay, so what is happening if I talk about this? See, if my tool is going to vibrate, instead of following a straight line trajectory, it is actually having some kind of a vibration. What is going to happen? See, when the tool is vibrating like this, and this is the surface of my workpiece. This is my workpiece surface, and this is the tool. Okay, I have assumed that okay, my tool maybe it has weared out, or my tool is not fitted properly. So if this is the trajectory, now you see when my tool is following this path, over here it is having a contact with my material. However, if when it is going like this, here it is not having any kind of a contact, then the contact increases. You know, because of this, the surface that is being produced on my workpiece, how is it going to be? It will be like this only, no? It is going to have a wavy nature as well. Right. So what is happening? It is not able to do the task it is supposed to do. Apart from that, it is also consuming more power as compared to when chattering was not occurring. Because see, initially without chattering, my system's work was only to cut out the metal or the workpiece. Right. Now it is also giving some vibration because of which is also getting dissipated in terms of noise. Right. So this is what this is taking excessive power to the input that is being given to the system. It reduces the efficiency of my system. Right. So definitely my chattering is an undesirable phenomena. I don't want any kind of a chattering because see it is even like giving a negative impact on my material. It is also wearing my tool. It is not giving me a precise workpiece after the whatever the process as it has been through. It is also consuming more power, not efficient. So definitely it's a undesirable thing, right? So the first option which says that it is desirable, it is absolutely incorrect. It is undesirable. Now the second option which says that it should be avoided, yes, this is the correct option. Third option which says that it may be observed in rolling operation. Yes, it can be observed in rolling operation, specifically in cold rolling operations. And the fourth option which says that It may also be observed in milling process. Yes, it can be seen in milling process. In case of milling process, chatter occur due to your improper fixtures. Fixtures, by fixtures I mean whatever be the fixing things that are being fixtures that are being used to fix the material and the tools. Okay. And then we have wear of tool. Likewise, there are other things also. However, you can, if you want to explore this, you can search it on, or you can read good books about manufacturing processes. Now, third question says that chartering causes. Okay, so as I told you that if this is my workpiece and this is the trajectory that my trajectory of tool, this is my workpiece, then what is going to happen? My workpiece is going to be like this. So this is the actual. However, all these are the exaggerated views. Okay, this is the actual, and I wanted to be, and this was desired. So what happened? Firstly, I wanted the surface to be a straight line. What has it become? It has become wavy. Second, I wanted a, let us say, thickness small h, but now I'm having a thickness capital H, which is not equal to small h. Okay, so what has happened? Chattering has led to the gauge variation. Now, by gauge variation, I mean that whatever I wanted my system, whatever the final dimension I wanted for my system, now because of the chattering, my operation has not been able to perform the task properly, and that is why there is a variation in the dimension of the workpiece. Okay, so it causes gauge variation. Second says that it causes corrugation. Yes, it causes corrugation. Corrugation means some wavy kind of a texture that appears on the surface of the your workpiece when any kind of a process is applied, manufacturing process is done on it, and it is due to chattering. Right. See here, you can see that it has led to the wavy surface, whereas I wanted a straight surface. Right, it has led to a wavy surface, so definitely it causes corrugation. And the third, which says that it causes surface imperfection, yes, it causes surface imperfection. Corrugation is also, you can say, a part of a surface imperfection, right? Because I wanted my surface to be smooth, and I wanted it to be straight, and I wanted the particular dimension. However, chattering has caused my corrugation and gauge variation, and it also causes surface imperfection. Like in this case, I have given an exaggerated view. It may happen that my vibration is very small as compared to the dimension. It is like this, something like this, you see. But then on a large scale, if I look at like that, I could maybe neglect the gauge variation. However, it has given surface imperfection. Right. The gauge variation I could neglect because the variation would be very small, but the surface is not perfect. It is imperfection. And the fourth one is noise. Yes, it is going to cause noise in the system. And I hope that that is a very self-explanatory thing, that definitely it is going to cause noise, right? Because there is this, uh, like if you have done any kind of a manufacturing process in your workshop, you must have observed that as soon as we try to make the contact, the first time there is a contact between the workpiece and your tool, there is some noise which is produced, right? However, there's also the noise when the manufacturing process or any kind of a rolling process or cutting process is happening. But initially, when they both come into contact, there is a very loud noise. I wouldn't say very loud, but there's a loud noise, right? Now, in this case, when my tool is actually vibrating, what would happen? Again and again, my workpiece and my this tool are coming in contact, breaking the contact, coming in contact, breaking the contact, coming in contact, breaking the contact. It will produce that kind of a noise again and again, again and again, right? And that is why it is going to produce noise also. Okay, so and these are the reasons that chatter is not desirable. You see, is there any positive thing about chattering? Nothing. Everything is negative. It has noise, it causes noise, gives surface imperfection, and it gives corrugation, gauge variation. You see that in manufacturing processes, there are two, three steps that we perform, right? Like the first step is not that good in precision, but we try to make the dimension near to what is required, and then we do many kind of a manufacturing process which is done just to get a precise dimension, perfect surface, shiny surface, right? And if we are going to use the tool like this, which has chattering in it, then what is the point of doing that finishing operation? There is no point now. So it is very important that the chattering is avoided so that my process is efficient and I get the desired result also. Okay, coming on to question number 4. Okay, so this is about the type of chatter. So firstly, how many types of chatter are there? So, depending upon the frequency range, chattering is divided into three categories, if you people remember. So, depending on the or musical octave of the natural frequency, comma, the types of chatter are the first one is your torsional chatter. So if you see that the different types of chatter, they are divided on the basis of the frequency range, right? So definitely your torsional chatter is the chatter wherein the frequency range is between 5 to 15 hertz, right? Then is your third octave chatter, and this is when your frequency is between 120 hertz to 240 hertz. And in third case, you have the fifth octave chatter, wherein you have your frequency range between 550 hertz to 560 hertz. Okay, so depending upon the frequency range, our chatter is divided. Now, see, if you look into the frequency ranges, you would get to know that, okay, which could actually be dangerous or produce more damage. See, if you remember, as I gave the basic definition of chatter, so in this case, there is a vibration in between the tool and the workpiece, which could be due to the many underlying reasons. However, there is a relative vibration in between these two, right? So now if you see, if I talk about the frequency range, so see if my frequency range is between 5 to 15 hertz, what is going to happen? The frequency is less. However, if the frequency is going to increase, you'll see that with the increment of frequency, the noise that is being produced is more. Why? Because this contract and losing the contact, it will happen at a faster pace with the increment of frequency. Right. Now, because of this, the surface imperfections would increase. Right. So eventually, and it is also dangerous. You see, the vibration at such high frequency, it is dangerous also, right? So definitely your B and C, which is a third octave chatter and fifth octave chatter, causes the most damage in the process, right? Which you could visualize also that with a higher frequency, the contact, the process of having coming in contact and then leaving the contact, it becomes very frequent with time, and due to this frequent occurrence, the variation in the gauge lengths and the surface perfection these increases, right? So the answer to these questions are B and C. Coming on to question number 5. Okay, so for the pneumatic artificial muscle, which of the following is true? Firstly, what is a pneumatic artificial muscle? Or should I say, what is artificial muscle? So we'll talk about natural muscle. So what happens in a natural muscle? So, for example, if I have my hand, okay, and I want to lift something. So, what is happening? Like, for example, this is my hand straight, and if I want to lift something, my hand is like this, right? Here, let us say that I'm trying to lift something, some weight. This is some weight, right? I'm lifting it. So, here, if you see what has happened, if you see, then you'll realize that I can model it something like this, that there was this muscle over here, and when I am lifting it, this muscle was something like this. It contracted, right? It contracted, because of which my hand was got folded about the elbow, and I was able to lift the weight, right? So this is how my muscle operates. If you'll see about the biomechanics also, you will see that your muscles are connected to your bones through tendons, and then your brain, which is your mastermind, gives signal to your muscle when you want to lift something that okay, now you have to reduce your length and increase your area so that you'll be able to lift a weight by your hand by rotating your hand about the elbow. Correct. So, because of this contraction of the muscle in the length direction and increase in the aerial direction leads to the effort that has been done by a human. Okay, so this is a natural muscle. Now, definitely, if we are calling it artificial muscle, it should be inspired by my natural muscle. So in that case, my artificial muscles should be something like that, that it should have the properties of my natural muscle, and it is able to perform the operation that my natural muscle is capable of performing, right? So my artificial muscle should be something like that only, that it should have some length and some area, and when I want to contract or when I want to lift something, it will contract in your length direction and expand in the area direction so that I'll be able to lift a weight, okay, or whatever, do the effort in doing some work, right? So inspired by this, pneumatic artificial muscle was introduced. Right. So pneumatic artificial muscle, you can say, is something like this. This is your muscle. Mm, this is your muscle. Okay. It could have different kind of a braid or these kind of a braids or anything. For now, we'll consider it something like this. Okay. And it is going to have some air in it. Like it would have some kind of a chamber wherein you could, let us say that this is a compressor by which you can supply air into it. Now, if you see that what is the working principle of a balloon? A balloon is when you inflate it, you give some air pressure into it and then it expands, right? Similarly, if I would give some air into this muscle, what would happen? My muscle would become something like, I should make it a, now you see, my muscle would then become something like this. Okay, this is after air is produced in the muscle. Okay, so this is your pneumatic artificial muscle. So if you see over here in a pneumatic artificial muscle, what did I do? I applied some air pressure inside it. Like I supplied some air inside it after using a compressor. Like I would use a compressor in order to compress the air, and then I will supply the compressed air into the artificial muscle. What would happen? It decreases in area and increases in the, sorry, it decreases in the length and increases in the area. This similar behavior, it is similar, it shows similar behavior as that of a natural muscle, and that is why we call it as a artificial muscle. Shows similarity in behavior with that of a natural muscle. Okay, so if you see that after applying the air, it reduces in area and increases the, okay, reduces in length and increases the area. Right. Now if I talk about the options, so the stiffness of the muscle is varied with the air pressure. Okay, so what do you think, whether it is right or wrong? See, first thing that you need to understand is that in case of a elastic, firstly, this is a viscoelastic material. Now, when I call a material viscoelastic, it means that it has elastic properties as well as it has viscous properties, right? So, if it has having elastic properties, it means that it is going to behave like a elastic material. Now, the elastic material's behavior is nonlinear, right? If you'll ever, if you try to stretch a rubber band, you'll observe that when you start stretching it, it is very easy to stretch it, right? You can easily stretch it up to some amount. But after some amount of stretching, this is the amount of force that is being required to stretch it further increases, right? It increases with the amount of the stretch, right? It becomes very difficult for you to further stretch the elastic band, right? Why? Because it's a non-linear system, right? It's a non-linear system. It's not a linear system, and that is the reason that it is very non-linear linearity that you can see during the stretching, which is due to the non-linear stiffness of the elastic material. Okay, so elastic material, if it has nonlinear stiffness, what does it mean? It means that with my deformation, my stiffness is going to change, either going to reduce or increase depending upon whether the material is my soft spring type or hard spring type, but it could increase or decrease, right? But the behavior is non-linear, right? So when I vary the air pressure, definitely my stiffness is going to change, because as I told you that my stiffness is varying with the deformation, and with my air pressure, the deformation is changing. So if my deformation is changing, then my stiffness should also change. Since it's a viscoelastic material, right? So the first option that says that the stiffness of the muscle is varied with air pressure is correct. Because it says, because when you vary the air pressure, your deformation is going to change, and if the deformation is going to change, your stiffness is going to change. Second option, the natural frequency of the system may be tuned by the air pressure. Now, if I talk about the natural frequency, if you remember that my natural frequency for a linear system would depend upon the mass and the stiffness. In this case, it would depend upon your pressure also, because it will be a nonlinear system, and pressure would also have some effect on the equation. However, if I for now consider that okay, there is no variation with pressure, but my stiffness is varying with pressure, right? That I've seen in the first option that okay, my stiffness is varying. But now I don't know whatever the equation of motion is, but I know that okay, my stiffness is varying. So if my stiffness is varying, it means that my natural frequency should also change. Correct? So the statement that says that the natural frequency of the system may be tuned by air pressure is correct, isn't it? Now we call it tuned because see, if I vary the air pressure, my natural frequency is going to change. Okay. So why am I calling it tune? I'm calling it tune because now it is in my hand. I know that if I vary the air pressure, natural frequency is going to change. So I want my system to maybe operate for a range 0 to A on the frequency axis, but my system is having the natural frequency at A by 2. So what would I do? I would just change the air pressure. I would then tune the natural frequency in such a way such that my natural frequency goes out of this zone 0 to A. And then I can apply the frequency 0 to A for the forcing function to the system, right? So when I say that tuning the natural frequency, I mean that I would either avoid going to the natural frequency, as it may lead to very high amplitude of oscillation, or where if I want that my system should have very high vibrations, very high amplitude vibrations, I want my system to operate on that particular frequency, but that frequency is not achievable by my system. So I would change the air pressure and I would tune the frequency in such a way that it would come inside the range of the this frequency that I could apply, and then I can actuate my system at the natural frequency. Okay, so this statement that the natural frequency of the system may be tuned by air pressure is correct. Now coming option on to option 3. So the time varying air pressure make the system parametrically excited. So if you people remember what is a parametrically excited system, so we had two kind of equations, like first one was x double dot plus omega n square x plus epsilon x dot. Let us say it is equal to f sine omega t. So this was my forced system, or externally excited system. Correct? But now what if I have a system wherein the parameter of, let us say, x is changing with time. The, what I mean is I have a system like this. Let us say that my epsilon is dependent upon x. For now, I'll just take it as 0. Now, this is my, actually, this is not the correct form. Let us just take it for now as 1 plus delta sine omega t. Okay, so now this is my parametrically excited system. So the answer says that the time varying air pressure make the system parametrically excited. So see, if you'll see, as sir has discussed it in the lecture also, so I will not go into depth much, but if you would see the equation of motion, you would realize that your air pressure has some multiplication with your variable. Okay, so if it is having some multiplication with your variable, what does it mean? It means that now if I try to vary my air pressure, what would happen? It would vary the coefficient of my variable, right? And my parametrically excited system is already a system wherein my variables vary with time. Correct. So the option that the time varying air pressure make the system parametrically excited is absolutely correct. Okay. Now the fourth option says that the air in the muscle increases area. No, this is not correct because if you see that when I have no, yeah, it is correct, right? Yeah, no, sorry, it is correct. Uh, we are talking about area and not length. So yes, it is correct because if you see over here, this is without air. This is your with air. So you realize that with the introduction of air into the artificial muscle, its length reduces and its area increases. So if I try to write it over here, that with introduction of air into the muscle, correct. So the option D is also correct that the air in the muscle increases the area. Definitely, it is going to increase the area. However, you'll observe that the variation, like I could consider the incompressibility constraint also over here. That due to incompressibility of the material, it may happen that the system's volume is going to be the same. So with the variation of my length, my area is going to vary with the incompressibility constraint. However, it is not always possible in case of materials. There may be some kind of changes. Like for example, if I have a braided muscle, it may happen that the because of the arrangement of the braids, the overall volume of my muscle, it also changes, right? Because the braids may align in such a way with the air pressure, right? So that could be a reason as well. And since it's an elastic material, so it may happen that it may contract or expand depending upon the air pressure and its material properties. So yeah, that is the case. I cannot uh, tell that yes, it is following the incompressibility constraint. Okay. Now coming on to question number 6. Okay, for the frequent, okay, I had to draw. I forgot drawing the. figure. Just a second. I'll just draw the figure. This is your amplitude, and this is going to be your frequency. Okay. And now if I plot the, this is my frequency response function. Okay, fine. It should be a bit smooth. I guess this is fine. Okay, correct. Now you see I'll have 2 points. This is R, this is B, and then we have these 2 points, S and Q. And if I extend these lines, this will be my A and this will be my B. Okay. So this is your amplitude frequency response. Now you people must have been familiar with this, that what is this amplitude frequency response? And this is because of the behavior of the like nonlinear behavior of the material. Because in case of a linear material, we'll have the amplitude frequency something like this, wherein we'll have a peak at wherein I'll have a peak at omega n, right? But in case of a nonlinear system, it may happen that my amplitude frequency response could be something like this or like this. It would incline in a particular direction depending upon the stiffness of the material, right? So these are the possibilities. Okay, so now I'll just first discuss about the figure and then we'll go into the options. Okay, so now see very clearly. If I follow the trajectory, something like this. See, if I start increasing the frequency, okay, so what trajectory would I follow? I'll go something like this from here. My this will keep increasing until and unless I reach this point. At this point, what is going to happen? At this point, my response is going to jump from here to here. And then I'll start going like this. This is your forward sweep. Okay. And now if I talk about the backward sweep, what is going to happen? So in case of a backward sweep, my system response would be something like this until and unless it reaches this point. See, it will follow the same line. However, in order to differentiate between the colors, I have taken it in this way. Okay. So from here, it would now jump like this and then it will follow this. Okay. And this is my backward sweep. Now, if you see over here that, okay, now we are very familiar with the jump up and jump down phenomena, right? This is my jump up. The system has jumped From SQ to Q, the system, the amplitude jumps from S to Q for a very small change of omega from B. Okay, during forward sweep. Okay, but the amplitude jumps down when the, okay, I should mention the points over here, to P when the frequency by a small amount from A. Okay, okay, during backwards. Okay, this is clear. We have already discussed it. Okay. Now, if I talk about that, okay, these are the changes that are happening, which is fine also. But what about the bifurcation? What kind of a bifurcation is happening over here? Right? That is also important. We know that now we are very clear with the jump up and jump down phenomena. But what about the bifurcation? We have all studied about the type of bifurcations and everything. But what about the bifurcation? What kind of a bifurcation is happening over here? So if you see clearly that if I talk about point S, what is happening over here? I'll just draw a exaggerated view. This and this. Right. I have this point S. No, I'll make it over here. Okay. Now this is my point S, and from here it is jumping to Q. So if you see, and from here it is jumping to P from R. So if you see among the all the values that are present over here of the amplitude, this part from R to S, the curve, my system is never achieving it. Correct? Why? It is never achieving it. Why? Because it's an unstable amplitude value. Okay, it's an unstable amplitude value. So if I draw the curve over here, it should be something like this. It should be something like this. So if you see that if my R to S is an unstable point, and if you look very closely, if you remember when we studied about bifurcation, we had a case of a saddle node bifurcation. Okay, it was the simplest kind of bifurcation. What was happening in it? A saddle node bifurcation was a bifurcation wherein a saddle point and a stable node, they were either coming together and they led to the vanishing of any of the equilibrium point, or there was a sudden generation of a stable and a non-stable branch. Remember, there was this kind of a bifurcation which we called as a straddle node bifurcation, either this or this. This we called as a saddle node bifurcation, wherein your this was stable and this was unstable. However, we studied it for your fixed points, uh, but this that is applicable for your dynamic bifurcation also, right? This is a dynamic bifurcation. The case that we are discussing over here, it's a dynamic bifurcation and not a static bifurcation. Why? Because the amplitude is varying, right? The amplitude is varying, that which means that my system is in a dynamic state, right? Okay, so now what is happening at point S? If you look closely at point S, you'll see that there is a stable branch from P to S, and then there is an unstable branch from R to S, right? So what is happening at point S? At point S, my one stable branch is colliding with another unstable branch, and after that, my amplitude vanishes, which means that at point S, my saddle node bifurcation occurs. Similarly, if you see at point R, you'll observe that before point R, there was only one equilibrium point. As soon as my system reaches point R, there is occurrence of a half stable point, right? And then after that, it leads to the occurrence of two branches, one stable branch and another unstable branch of amplitude, which means that at point R, saddle node bifurcation has happened. I hope that whatever I'm trying to say is clear. And this is a dynamic bifurcation. We call it dynamic bifurcation because in this case, our amplitude is varying. We are having a stable amplitude, we are having an unstable amplitude, and this stable and unstable amplitude come together to lead to a saddle node bifurcation. So I would write it like a stable amplitude branch and an unstable appear at point S, which signifies that Sn or your saddle node bifurcation occurs in case of a and similarly, okay, I have written it wrong, right? At point S, they disappear. Here it should be disappear and are one stable and one unstable branch of the amplitude appear, which is your saddle node bifurcation. Okay, so this was the second concept. Now we'll come on the third concept, which is what? Your basin of attraction. Firstly, what is a basin of attraction? See, we define the basin of attraction in such a way that I would know that with the change of initial condition, where would my system go to? Right. So, what do I do in this case? I take a set of initial conditions. Like in the x-axis, I would plot my initial condition x naught. In the y-axis, I would plot the initial velocity x naught dot. Okay. And I would just take those points and I would simulate my system and I would see that where is my system going. Like in this case, I have three amplitude values, right? Two are stable and one is unstable, right? So what if I try to vary my initial condition and I keep everything as constant? Do you understand? All the parameter values are kept as constant. Let us say that I take the value like this over here, something over here. I'll just take a plus b by 2 frequency. I've considered a plus b by 2 as my frequency. Now, if I want to know that if I keep all the parameter values constant and now if I vary the initial condition, how is my system response going to vary? Which means that which amplitude is it going to achieve? Whether it will achieve some amplitude, your this, which is your, I'll call it as A1, A2, A3. Okay, you have three amplitudes A1, A2, A3. So if I change the initial condition, is my system going to have always going to have the amplitude A1? Or is it going to sometimes have the amplitude A3 or it could have the amplitude A2? So now see, in this case, firstly, A2 is your unstable amplitude. First, I'll just write it. My A2 is unstable amplitude. Now, what is the property of an unstable fixed point? If my system is starting from the unstable fixed point and there is no forcing on the system, my system is always going to remain at that unstable fixed point. Simple. But even if there is a very small variation in the initial condition from the unstable fixed point, my system is never going to come back to that fixed point. Similar is the case for amplitude also, dynamic case also. If my system is starting from an initial condition which is in the trajectory of the amplitude A2. Now, by this I mean is like, for example, if my amplitude, my response will be A2 sine A plus B by 2 into T, right? So at T0, my X naught will be what? It will be 0. Let us not talk about 0 because T0 is a very trivial case. I'll take as 90. So then my X naught is going to be what? A2. So if my initial condition is in the range of A2 in a circle, it lies on the circle, not inside or outside, lies on the circle with the radius A2, then my system is going to achieve that equilibrium, like this. But if it does not, then, well, it is never going to achieve that. It is not possible also. This I just gave you an example, but in practical systems, since this is a forcing case, my system is going to diverge from that place. This thing would be done if my system is, I would say, not forcing and without damping. Then this could be possible. But if my system is a forcing, then what is going to happen? It is going to diverge from that point. So A2 never going to achieve. Okay, it will not achieve A2. Now comes the A1 and A3. Okay, so now when you'll do the numerical simulation and you'll plot and you'll see that the variation, how is it changing, you'll get some interesting patterns. right? With the variation of different parameter, that how my system is going to, what are going to which kind of a periodic response, and how the attractor is changing with time. So that is why we plot the basin of attraction, so that we know the range of the initial condition in which my system is going to achieve the oscillation with amplitude A1, or when it is going to achieve the oscillation of amplitude A3. Okay, so in your basin of attraction, you have your X naught, which is your initial. Okay, and then you will plot the basin of attraction over here. Okay, so if I would ask you that how many equilibrium points are there, how many stable equilibrium points are there, how many unstable equilibrium points are there, so by the basin of attraction you'll get to know. Like in the case of this, as I tried to relate it with the amplitude frequency response, it was easy to for me to identify that okay, my A2 was my unstable amplitude, so it is never going to achieve. However, if I don't know, then at earlier stage that okay, this is going to be the amplitude frequency response, then in that case I'll have to plot the basin of attraction. Okay, I hope that this is clear. So coming on to the options. The system has three amplitude between A and B. Between A and B, three amplitudes. Yes, it is correct. However, the three amplitude among the three amplitudes, one is stable, one is unstable, and the two are stable. Three amplitude, we'll write one unstable plus two stable. The system undergoes SN bifurcation at points R and S. So as I have shown you, yes, the system undergoes the saddle node bifurcation at R and S. However, the direction is different. In one case, the stable and unstable are coming together and vanishing, and in the other case, there is the occurrence of two branches, one stable and the other one unstable. The response jump from P to R during forward sweep. During forward sweep, my response is going from P to R? No, because during the forward sweep, my system is going to, during forward sweep, my system is going to jump from S to Q. It is very important that you remember that during the sweeping of the frequency, the system is always going to follow the trajectory up till the point that there is some here, there is some jump criteria. It is not going to jump from here. It is always going to jump from this discontinuity, sort of discontinuity, I would say. Okay, here you can see that there is a change of slope. There is a change in the sign of the slope, and at that point only, it is going to show this kind of a. Yeah, so this is not correct. So only A and B are correct options. Okay. Okay, this I have already discussed. Question number 7, and I hope that you'll people understand this now. So, which of the following is correct regarding the basin of attraction of the figure in the previous question? There are three stable amplitudes. There is one unstable amplitude. There are two stable amplitudes. So, the plot was something like this. Should make a bigger plot over here because we have space also. Okay, so this was your plot. So now if you see that in this range, which was your A and B, you had three equilibrium point, wherein your two were stable and one was unstable. However, apart from this, on the frequency axis, there was only one equilibrium point. Okay, so I forgot to mention over here which of the following for the range of frequency from A to B. There are three stable equilibrium. Oh, there are three stable amplitudes. No, this is not correct. There is one unstable amplitude. Okay, there are two stable amplitudes. These B and C is going to be the right answer. Okay, I hope that this is clear now. Okay, we have discussed it a lot of times, and I think now you people will be able to counter a question if something comes like this. Okay, so the question says that the shear modulus of a material is given as this. The material is okay. So when my material is viscoelastic, no, I define, not I, it is the shear modulus is being defined in a complex form so that one could relate between the elastic property and the viscous property of the material, because you see that if my material is viscoelastic, it is going to have some elastic behavior along with some viscous behavior, but which one is dominant, right? It may happen that the viscous effect is very less, so in that case we could neglect the viscous effect and we could just consider a linear damping in it. But if in some material the viscous effect is very high, then in that case we cannot neglect the viscous effect. We need to consider the viscous effect. Now, if my material is having a viscous effect, you realize what is going to happen. It is going to damp out, right? It is going to damp out the vibrations. And that is why that the material is going to reach the equilibrium state. Like we like model viscoelastic material using a spring mass dashpot system because it has both the properties of a elastic material and a viscous material. Okay. So, and like I said, that if my material is not that much viscous, it is more elastic. So, in that case, I can just maybe consider my damping coefficient to be very less, or I could just neglect the damping also. I can just consider the mass in the spring, right? So, in case of a for a viscoelastic material, your G is going to be G1 plus I into G2. Okay, wherein your G1 is your storage modulus, which accounts for the elastic energy stored in the system. And your G2 is your what? Dissipation modulus. Because you see your viscous effect, your dashpot is going to dissipate energy, right? So this is your dissipation or viscous modulus, and it accounts for the energy dissipated as heat. Okay. So now, what do we define? We define the ratio of G1 and G2. Like we define a phase angle tan delta as G2 by G1. Okay, and on the basis of value of delta, if delta is close to 0, then my material is what? Close to 0 means that my tan of delta is close to 0. So my G2 is very less as compared to G1. So my material is less viscous and more elastic. Material is material is more. You see, near to 90-degree means that your G1 is very less as compared to G2, right? So the viscous effect of the material is very high as compared to the elastic property. So my material is more viscous. So the question says that the shear modulus of a material is given as 6000 plus I into 3000. So my in this case my G1 is what? G2 is what? So if I try to find G2 by G1, what is it going to be? 1 by 2, which is equal to 0.5. So if I try to evaluate this, which would be tan inverse of 0.5, it is close to 0. I won't say that it is rounded off to 0 or nearly equal to 0. If I get any number, I have to make a choice by deciding whether it is more close to 0 or more close to 90-degree. Okay, we don't have to think about the round off, but we have to see that it is more close to 0 or more close to 90-degree, and whichever it is close to, we can then give our conclusion. Okay, now these are all relative terms. Okay, these are not very rigid terms. So it would depend upon the material. Okay, so in this case, however, I would say that my material is more what? Elastic, right? Okay, now coming on to the last question. Which of the following may be used for control of the chaos? Okay, so as I've told you that there are various kind of a controllers that could be used for controlling of the chaos, and by controlling of chaos, we means that we could regulate it, we could stabilize it, or we could track it, or we could apply a synchronization on it so that it would show lesser sensitivity towards the initial condition. So for the question, if all the three answers are correct, I would not go much into this because these are all related to control topics. PID is your proportional integral derivative controller, and it's a linear controller which may be used for controlling of chaos. Then you have adaptive controller. Now by adaptive, I mean that in case of a PID controller, I have gains like KP, KD, and then I have KI. So in case of adaptive control, like in case of PID controller, these are fixed, while in case of adaptive, KP, KD, and KI vary with the system response or with the time. So it varies with time. It is not constant throughout. So because of which, if my error reduces, my these values also reduces. So it would lead to a decrease in the energy that is required for the controlling of the system. C option, we have a SMC controller. SMC is a sliding mode controller. It's a nonlinear controller. It is also very effective and can also be used for controlling of the chaos. So all the three answers are correct. And these are all related to control systems. So discussing it is not much important. However, I want to mention certain things that in this live session, I have taken all the mostly theoretical questions. Reason being that in your assignment problems, if there is any computation or any kind of a numerical related problem, you can get the answer by referring to the lecture or by applying the code. Since the equation that has been given, if I would have used it directly to solve the MATLAB through the MATLAB, then that would be not right, since that assignment problem is yours and you have to solve it on your own. And I guess I have trained you much. However, I don't know, but I have given my best in training you with the MATLAB and how to deal with the differential equation. I've taken sufficient examples also. And apart from that, if there are any questions which are related to the papers, so you could definitely refer to the paper for answering those questions. And I have tried to make your concept clear, which would help you to solve the assignment problem, and anyways, which would help you for the uh, bigger problems of nonlinear dynamics, which you would be solving in your courses or maybe in your research topics or wherever you would be. Uh, Apart from that, if you have any queries, you can ask me. Also, this is our last live session. However, I have scheduled a extra session for tomorrow of 2 hours, wherein I will be giving a brief overview of whatever we have been learning since the last 12 weeks. And no, so definitely, if you have any doubts, you can ask me. I want it to be an interactive session so that it would be very helpful. However, I'll just go through whatever we have learned in the previous classes. Apart from that, from today's lecture or before any lecture, if you people have a doubt now, you could ask me, or otherwise, we'll just conclude the session.
Thank you, madam.
Okay, thank you. Please, if you have any doubts, come with it tomorrow. And tomorrow is going to be our last session. So that is all that I want to say.
Madam, one doubt is there.
Yes, please.
With respect to that bifurcation diagrams,
Yes,
usually in x-axis we will be having control parameters, and the
yes.
y-axis we will be having some response, right? But in
Okay.
case where you explained about this duffing frequency response plot.
You're talking about this
Yes,
question number
yes, ma'am,
6?
yes.
Yes, yes.
No, usually this x-axis and y-axis, no, I'm getting confused because most of the bifurcation diagrams, x-axis
Hmm.
will be having control points and y-axis will be having not the response. It will be something like um, amplitude, right? Amplitude of input amplitude. Is it input amplitude or output amplitude?
Output. Output, not input.
Uh, Okay, madam. With respect to stability chart, we'll be
Hmm.
having in x-axis and y-axis. For example, parametrically excited system.
Hmm.
In x-axis, we will be having frequency, and y-axis we will be having input amplitude.
No, we have output amplitude.
Uh,
Input amplitude, if we vary the C in bifurcation diagram, I think there is some uh, you're getting confused somewhere, if I'm able to understand. Otherwise, I'll just try to explain you once. Then, if you have the same doubt, then you can ask me. Okay. So, in case of bifurcation diagram, we change the parameter and then we check that what is the variation in the system response. As you said that on the y-axis, if we plot the input amplitude, then how are we actually checking the system response? Input, we are not concerned about the input. We want through bifurcation diagram, we want to know that with the variation of a parameter, with the variation of a certain coefficient, how is my output changing? How is my system response changing?
that I understood for static bifurcation analysis. For a
Okay.
dynamic or parametrically excited system,
Mm-hmm.
we are having one more input, which is input amplitude.
Yes.
Uh, how we will account that in the bifurcation chart or stability chart?
Okay. So see, when we are talking about bifurcation, first thing is that we vary only one parameter. Apart
Okay.
from that, every parameter is kept constant. So as you said that yes, we have a input amplitude also. So what I can do in this case, I have kept my input amplitude constant and I have just varied the frequency. What you are saying is also correct, but if for that case I would have to keep my frequency constant and then I would change my input amplitude and then I can again plot. In that case, my x-axis, if you uh, my x-axis is going to be my here. My x-axis is going to be my input amplitude and my y-axis is going to be my output amplitude. Okay,
Yes.
likewise, I can find the bifurcation diagram with other parameters also, but it is very important that if we want to study that with the parameter how my system response is changing, I keep all other parameters constant and I only vary one parameter. Am I able to
Yes,
answer
madam.
your question?
Yes, madam, I understood. And one more
Oh,
thing in this
yes.
deafening frequency response,
Mm-hmm.
uh, usually I was earlier having thought that unstable means it's not safe, but it's not like that. Unstable means it will never be achievable. That amplitude cannot be
Yes.
achieved. That's what you
Yes.
meant in this explanation, right?
Yes. But see, it is not always correct. I mean, in this case, my unstable is safe, correct?
Yes.
But it could be not safe. Now you would ask, how is it not safe? So see, if in this case my unstable point is bounded by two stable points, correct? So that
Yes.
is why it is safe. However, if my these two stable points, let us say that my upper stable point is very high. What if it is maybe in kilometers? Then in that case, if I talk about the deformation of a beam, if it goes into kilometer, it is unstable.
Okay.
Right. Although it's an equilibrium point, but I don't want my beam to go and deform into kilometers. Okay, so it would depend upon perspective. However, if it is 1 meter or not even 1 meter, 1 mm, then yes, it is stable. So it would depend upon the bound, and it may happen that I don't have any bounds. In that case, also it is unsafe. Usually, we say that unstable point is not safe because in that case, my system will try to reach out to some stable point. And if my stable point is at a very distant place, then it would cause catastrophic failure or instant damage to the system.
Yes, madam, I understood. Thank you, madam.
Okay, thank you so much. Okay, we'll meet tomorrow then.